How do logical qubits create scalability issues in quantum error correction? Imagine trying to build a giant puzzle with thousands of tiny pieces. Each piece needs to fit perfectly, or the whole picture falls apart. That's similar to what happens when creating logical qubits in quantum computers. Logical qubits are made by spreading one piece of quantum information across many physical qubits. This helps protect against errors caused by noise or decoherence. But it also makes building large quantum systems much more complicated. To make one logical qubit, you often need hundreds or even thousands of physical qubits. The exact number depends on how noisy the physical qubits are and what error correction could you use. For example, some codes might need just a few hundred physical qubits per logical qubit, while others could need over 1,000. This means that as you want more logical qubits to run complex algorithms, the total number of physical qubits skyrockets. That's a big challenge because hardware resources are limited and expensive. Error correction involves more than just encoding information. It requires frequent operations called quantum gates and measurements on the physical qubits. These operations are needed to detect errors and fix them quickly. But as the system gets larger, controlling all these operations becomes harder. The circuit depth, or how many steps are needed, increases. More steps mean more chances for errors to sneak in, especially if the hardware isn't perfect. So, the process of error correction adds a lot of operational overhead, making the entire system slower and more complex. Managing the entanglement among many physical qubits is another big hurdle. Entanglement is what keeps the physical qubits linked together so they can act as one logical qubit. But noise and decoherence can break these links. Keeping the entanglement stable across hundreds or thousands of qubits requires very advanced hardware and extremely low error rates. If the hardware isn't up to the task, the error correction can fail, and the logical qubit's integrity is lost. In summary, logical qubits create scalability issues because they need a huge number of physical qubits. The error correction protocols add operational complexity and requiring precise control. Maintaining entanglement across many qubits is very challenging. As the number of logical qubits grows, the hardware and resource demands increase exponentially. That's why making large, reliable quantum computers is such a tough challenge today. Researchers are working hard to develop better error correction codes, improve hardware quality, and find smarter ways to encode information, all to make logical qubits more practical for larger systems.